Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. Today, we are going to solve few problems based on the topic laser. The questions or the problems on the laser were picked up from the GATE Physics paper 2021. Before going to solve the problems or the questions on the laser, we will be discussing very briefly about the theory of laser and its application. So let us start our discussion on the topic laser. What is laser? The full form of the laser is light amplification by stimulated emission of radiation. So this full form suggests that laser is basically amplification or enhancement of light intensity by a physical process, that is stimulated emission of radiation. So the principle of laser is entirely based on the phenomena of stimulated emission of radiation. So this phenomena is our key point or very important thing to understand this physical process laser. So we'll be discussing this stimulated emission of radiation in very details in the upcoming slides. There are three atomic transition mechanisms which are involved in laser. So let us understand those three mechanisms first. The first mechanism is excitation of atoms, which is also known as pumping. So what is excitation of atoms? So let us consider some atoms are at the ground states. Now we apply some energy, that may be electrical energy or maybe optical energy or something else. So the atoms will absorb the energy. So basically electrons in the atoms will absorb the energy and they will be excited to the higher energy levels. This is known as excitation of atoms or pumping. Now the second one is spontaneous transition from an excited state to a lower state. So we have seen in the first point, that is excitation of atoms. So in this case we are applying some energy to excite the electrons to go to a higher energy level. Now the excited electron will not stay at the excited state for lifelong. There are certain time scale after which the electron will be de-excited and it will come to its ground state. This is known as spontaneous transition from an excited state to a lower state. Now the third one is induced transition from an excited state to a lower state, which is known as stimulated emission of radiation. Now this phenomena, induced transition, is completely different from these phenomena, spontaneous transition from an excited state to a lower state. So this spontaneous transition is completely random process. We don't have any control over it. But this induced transition is basically can be triggered by external factor. So we can trigger with some external energy to induce this kind of transition. So we'll understand in the upcoming stage how can we get this stimulated emission of radiation and why it is important in the case of laser. In the previous slide, we have already discussed about the three atomic transition processes which are involved in the laser. We'll again visit that three atomic transition processes in details. We'll construct some mathematical equations for each processes and we'll connect those equations to construct the basic theory of laser. So the first process was excitation of atoms. Let us consider two energy levels, that is E1 and E2. The energy gap between these two energy levels is E2 minus E1. the equivalent photon energy is H nu 12. We can consider this energy level E1 as ground state and the energy level E2 as excited state. Let us consider the number of atoms per unit volume at the ground state or energy level E1 is N1. Now the probability of the transition from this energy level 1 to energy level 2, that is 1 to 2, is B12. The rate of excitation from the energy level 1 to 2 is given by R1 to 2 equals to B12 times N1 times U nu. Here B12 is the probability of transition from the energy level E1 to E2. N1 is the number of atoms per unit volume at the energy level, that is ground energy level E1, and U nu is basically the energy density of incident EM radiation having the frequency nu12, that is basically E2 minus E1 by H. Here H is the Planck's constant. So this rate of excitation, this equation will be used in the later stage. Now the second atomic transition phenomena was spontaneous transition from excited state to lower state. Now we have learned about the excitation of atoms. So after the excitation, the number of atoms per unit volume at the excited state E2 will be N2. The lifetime of the excited state is around 10 to the power minus 8 seconds. So this is the time scale up to which the atoms can stay at the high energy level after excitation. And when the atoms will come to this ground state after de-excitation, it will release the energy H1 nu 12. Now, in spontaneous transition or emission process, the emitted light is incoherent in phase. The probability of the spontaneous transition from the energy level 2 to 1 is given by A21. The rate of spontaneous transition is given by R from 2 to 1 with a superscript SP equals to A21 times N2. Here N2 is the number of atoms at the energy level E2 per unit volume. Here SP superscript corresponds to the spontaneous transition. Now the third atomic transition process was induced transition or stimulated transition from an excited state to a lower state. In this case, the excited atoms are triggered by an external photon energy H nu 12, which is basically the energy gap between these two energy level E2 and E1, so that the excited atoms will be de-excited to its ground state energy level. So as a result, we will get the released energy which is equal to H nu 12. So effectively, we are applying here a single photon with energy H nu 12, and as a result, after de-excitation of the atoms, we will get two photons with the same energy H nu 12, and the emitted light will be in the same direction and phase coherent. The probability of the transition from 2 to 1 energy level, the induced or stimulated transition, will be B21. The rate of this kind of transition is given by R from 2 to 1 with a superscript ST equals to B21 times N2 times U nu. So, we have obtained three coefficients A21, B12 and B21 while discussing the three kind of atomic transition processes. Those are excitation of atoms, spontaneous transition and induced transition or stimulated transition. These three coefficients are known as Einstein's A and B coefficients. Under equilibrium, the rate of upward and the downward transitions must be equal. So from the equilibrium condition, we can write this R from 1 to 2 that we obtain from the excitation of atoms equals to R from 2 to 1 Sp plus R from 2 to 1 St. So this is the rate of transition for spontaneous transition, and this is the rate of transition for stimulated transition. So we'll put these R from 1 to 2 and R from 2 to 1 for the case of spontaneous and stimulated transition, which we have already obtained in the previous slides. After that, we will get B12 times N1 U nu equals to A21 N2 plus B21 into U nu. So after some rearrangement, we will get an expression for U nu, that is the energy density for the incident EM radiation, that is U nu equals to A21 divided by B21 times 1 by B12 by B21 times N1 by N2 minus 1. Now we can write N2 divided by N1 equals to exponential of minus E2 minus E1 divided by kBT. This relation comes from the Boltzmann distribution law, which is given by N equals to N0 times exponential of minus E by kBT, where N is the number of excited atoms at an energy level E. N0 is the number of atoms per unit volume at ground state energy level E equals to 0. Now E2 minus E1 is the H nu, that is the photon energy equivalent to the gap between two energy level E1 and E2. So we can write N2 by N1 as exponential of minus H nu divided by kBT. So we'll use this relation in the equation of energy density for EM radiation, that is U nu equals to A21 divided by B21 times 1 divided by B12 by B21 times exponential of H nu divided by kBT minus 1. Again, we know the Planck's radiation formula is given by the U nu equals to 8 pi H nu cube divided by C cube times 1 by exponential of H nu kBT minus 1. So this relation which we have obtained for the case of laser must agree with the Planck's radiation formula. So by comparing these two equations, we will get B12 equals to B21 and A21 divided by B21 equals to 8 pi H nu cube divided by C cube. So these relations are known as relation for Einstein's A and B coefficients. Now we will understand how does the stimulated emission or the induced transition help in the laser production. For this, we will consider all the atoms are in the excited state, that is the energy level E2, and the corresponding ground state energy level is U1. Now we consider a single photon with the energy H nu, that is equals to E2 minus E1, is incident on that system. So this single photon will trigger one of the excited atom to have the transition from the higher energy level E2 to lower energy level E1. So that is the stimulated emission process. So as a result, we will get two photons having the same energy H nu. Now these two photons will again trigger another two excited atoms to have transition from the high energy level to the low energy level. So after that stimulated emission process, we will get 4 photons, and again these 4 photons will trigger 4 another excited atoms, and as a result we will get 8 photons, and this process, stimulated emission process, will go on. So this gives amplified stimulated emission, and for this we need sufficiently high number of excited atoms in this system. According to the Boltzmann distribution law, we have seen N2 divided by N1 equals to exponential of minus h nu divided by kBT. So normally the number of atoms in the upper energy state E2 is much lower than in the lower energy state E1, that is N2 very less than N1. But for amplified stimulated emission from the energy level E2 to the energy level E1, we must have N2 greater than N1. So this condition is known as population inversion. So hence we can say first we need the population inversion, and this will give the enhanced stimulated emission, and this will give the laser effect. So this population inversion is the essential criteria to have the laser effect. Now we will briefly discuss how population inversion can be achieved. So there are several methods to achieve the population inversion. We will discuss few of them. First one is optical pumping. So this process is usually used in ruby laser. This is nothing but the excitation of atoms. So if we externally excite the atoms, so more and more atoms will be in the excited state rather than the ground state. And second one is excitation by electrons, which is usually used in gas laser. So what people do in this case, the gaseous system is heated by high energetic electron beam, so that the electrons energy will be absorbed by the atoms and they will be excited. So we will get more and more gaseous atoms in the excited state. And the third process is inelastic collision between atoms. So in this case, two different kind of atoms X and Y are forced to collide in an inelastic manner, so that one kind of atoms will transfer the energy to the another kind of atoms. So the second kind of atoms will be excited. So we'll get more and more second kind of atoms in the excited state. Now we'll briefly discuss about a special type of laser, which is ruby laser. Ruby is basically a crystal of aluminum oxide. If we see the energy levels, then the ruby is a 3-level system. So there will be 3 energy levels. The energies of the energy level are denoted by E0, E1 and E2. Here the energy level having energy E1 is considered as metastable state. So metastable state is basically the excited state having a longer lifetime than the usual or ordinary excited state. Now we will see what are the atomic transition processes are happening in the case of ruby laser. So first one is excitation from the energy level 0 to 2. So that is the transition from this energy level to this energy level. So when we apply some photon energy h nu, which is equals to E2 minus E0, then some atoms will be excited to the energy level E2. So this process is known as optical pumping, but this excited energy level has some lifetime of the order of 10 to the power minus 8 seconds. So after excitation, the atoms will be de-excited and they will come to this energy level E1. So this process is known as spontaneous emission. Now this energy level 1 is our metastable state. So as state 1 is metastable state, atoms will be trapped at that E1 energy level for longer time, and the time scale is usually longer, that is 3 into 10 to the power minus 3 second. But this excitation process from the energy level E0 to energy level E2 will continuously go on. So after some time we will achieve the condition, that is the N1 greater than N2, that is the number of atoms at this metastable state will be greater than the ground state, that is E0. So this condition N1 greater than N2 is known as population inversion, that we have discussed in the earlier slides. Now if we can achieve the population inversion, then we can easily get the enhanced stimulated emission, and that process will happen in between the energy state 1 from 1 to 0. So we understood how the laser effect happens in the case of ruby laser. This question was asked in the GATE Physics paper 2021. This is a MSQ, that is multiple select question having 1 mark, and this question was asked from the topic atomic physics, specifically from the chapter laser. According to the question, to sustain lasing action in a 3-level laser as shown in the figure, the necessary condition or conditions is or are, there are 4 options given. First option, option A, lifetime of the energy level 1 should be greater than that of the energy level 2. Option B, population of the particles in level 1 should be greater than that of level 0. Option C, lifetime of the energy level 2 should be greater than that of the energy level 0. And the last option, option D, population of the particles in level 2 should be greater than that of the level 1. So there are 4 options given. Now as this is MSQ, so it is highly possible to have multiple options correct for this question. So let us see how to solve this problem. In the case of 3-level laser system, we know one intermediate state is required between the ground state and the excited state, and the intermediate state is basically metastable state. In this case, the energy level 1 lying in between the energy level 0 and 2 is our metastable state. To sustain the lasing action in a 3-level laser as shown in the above figure, the necessary criteria are: the first one is lifetime of the energy level 1 should be always greater than that of the energy level 2. So this condition is very important to have the lasing action, because after excitation of the atoms from the energy level 0 to 2, the spontaneous transition will happen from energy level 2 to 1. Now, if the lifetime of the energy level 1 is very greater than the lifetime of energy level 2, then the most of the atoms coming from the energy level 2 to 1 will be trapped in this energy level 1. So, this criteria is required to have the second criteria, that is known as population inversion, that we will see in the next slide. The second criteria is population of the particles in the energy level 1 should be greater than population of the particles in the level 0, that is in the ground state. So this condition is known as population inversion, which can be achieved in between the energy levels level 1 and level 0. This will lead to the enhanced stimulated emission, which is the most important process required to have lasing action. So ultimately we will have the laser in this process. So the option A and the option B are the correct for this question. So we have solved this problem and we found that option A, that is lifetime of the energy level 1 should be greater than that of the energy level 2, and the option B, that is population of the particles in level 1 should be greater than that of the level 0. These two options are the correct options for this question. This question was asked in the GATE Physics paper 2021. This is MSQ having 1 mark, and the topic of the question is atomic physics. This question was asked specifically from the chapter laser. The question is, consider the atomic system as shown in the figure, where the Einstein A coefficients for the spontaneous emission for the levels are A from 2 to 1 is 2 into 10 to the power 7 second inverse, and A120, that is 10 to the power 8 second inverse. If 10 to the power 14 atoms per centimeter cube are excited from level 0 to level 2, and a steady state population in level 2 is achieved, then the steady state population at level 1 will be x multiplied with 10 to the power 13 per centimeter cube. Then we have to find the value of x in the integer form. So let us see how to solve this problem. So according to the question, we have to deal with the 3-level laser system. Some informations are given. Those are: transition probability from the energy level 2 to 1 is given by A21 equals to 2 into 10 to the power 7 second inverse. Transition probability from the energy level 1 to the energy level 0 is A10, that is 10 to the power 8 second inverse. It is also given number of atoms per centimeter cube excited from the energy level 0 to 2 is N2 equals to 10 to the power 14 per centimeter cube, and a steady state population is achieved. We have to find the steady state population at energy level 1, that is given by x into 10 to the power 13 per centimeter cube. So we have to basically find the value of x such that we get the steady state population condition in that system. Now let us consider the population at energy level 1 is N1. The rate of transition from the energy level 2 to energy level 1 per centimeter cube is A21 times N2. The rate of transition from the energy level 1 to energy level 0 per unit volume, that is centimeter cube, is A10 times N1. The rate of population at the energy level 1 is then given by dN1 dt equals to A21 times N2 minus A10 times N1. Now at the steady state, we will have dN1 dt equals to 0. So from here we can write A21 times N2 minus A10 times N1 equals to 0. So after little rearrangement, we can get N1 equals to A21 times N2 divided by A10. Now these three values A21, N2 and A10 are given in the question. So we'll put the values in this equation. So we'll get N1 equals to 2 into 10 to the power 7 times 10 to the power 14 divided by 10 to the power 8. So we are getting N1 as 2 into 10 to the power 13 per centimeter cube. So the value of x in the integer form is 2. So 2 is the answer for this question. So we have already solved this problem, and we found that the steady state population at level 1 will be x multiplied with 10 to the power 13 per centimeter cube, where x value is 2 for this question.